Hey, welcome back to Physical Science. Today what we're going to be doing is going over acceleration, but this time we're going to do is go over acceleration when it is vertical. Hopefully you've already looked at that video I sent to you where they dropped a bowling ball and a feather and they vacuumed out a huge chamber. And that scientist went over with you how everything falls at the same rate, and he explained why. Today what I'm going to do is go through a couple examples of calculations that you have to know how to be able to do. Okay? And we're going to use our acceleration question, our acceleration information, but we are going to be doing that in a vertical instead of horizontal. Okay? So, just got a couple examples to go over, and then hopefully there'll be a handout for you that is attached. All right, here's our question. Question number one. Question number one is, if a rock is dropped off of a cliff. Now, of course, all these questions are no air friction, okay? There will always be no air friction. If a rock is dropped off a cliff and it takes 7 seconds for it to reach the ground, then what is the velocity when it arrives at the ground? Okay? So this rock right here, when it gets dropped off of that cliff right there, of course, when it first starts, its velocity right there, when you first let go of it, the velocity is 0. Okay? Because it's not really moving. When you first let go of the thing, it's instantaneously is going still. Or it's going still. It's remaining still just for while you got a hold of it. And when you first let go of it, then it begins to drop. And of course, you already know by your personal experience, it starts to speed up and go faster and faster and faster until it reaches the ground. Now you know that as this thing goes and it keeps on accelerating, going faster and faster and faster, that acceleration, what exactly is pulling that rock towards the ground on here, of course, is the acceleration of gravity. Gravity, our Earth is pulling on that rock, and it pulls on your body, it pulls on anything that has mass on it, and it pulls that down with a certain amount of force to it. Now, one thing we've got to know about this acceleration right here is that acceleration of that rock, or it could be a feather. Remember, we're saying no air friction. It could be Grandpa's old Buick. Whatever it is we're dropping off of this thing, it all has the exact same acceleration. So if you drop this rock on Earth, then what will happen is every 1 second that goes by, that rock is going to gain 9.8 meters per second, going faster and faster and faster. Which means every second this thing drops, it's going to gain another 9.8 meters per second. Every second that this thing drops, it's going to gain another 9.8 meters per second. So at first it's going 0, and then it's going to be going 9.8 meters per second after the first second. After the second second, it's going to be going 9.8 plus 9.8. So it's going to be going down here. It'll be going 19.6 meters per second. Okay? But it gains 9.8 meters per second every second that it drops. Okay? So again, it doesn't matter if it's a rock, Grandpa's Buick, a feather, doesn't make any difference. That acceleration is going to stay the same. And that acceleration right there is always going to be 9.8 meters per second. Okay? Squared. Because acceleration in seconds is squared. So that is very, very important right there. That 9.8 meters per second squared is very, very important. That is true on Earth. Now, if you look at that acceleration on the moon, it's going to be 1/6 that. On Mars, it's like 3.7. So on future trips to Mars, our astronauts go out there, they'll be a lot lighter on the Mars because there's a lot less acceleration of gravity, a lot less pull on the planet, on their bodies. Now, the only other thing I want you to add to this is, since this is all going downward, remember something in physics. Direction is very important. So the positive and negative on numbers always tells us the direction that things are going. So since this is going downward, in your math class, when we talk about things that go down, then we always say it's negative. So this is going to be negative 9.8 meters per second squared. Now this acceleration is the same for, again, for a rock, a Buick, rockets, whatever it is. Anything that falls, it's got a negative 9.8 meters per second. So this acceleration right here is very, very special. It's not just any old A. So we're going to take this A right here, and since it's a special A, we're going to change it into G. And that G right there is very, very important because you've actually heard about that G before. When you go on a amusement park ride and you go down around the loops and you feel that really strong pull on your body when you're in the cart, you're experiencing a certain number of G's. In other words, you're experiencing a certain number of gravitational accelerations. In other words, if you're pulling 3 G's, that means you're pulling 3 times 9.8 meters per second squared. In other words, it'd be like 3 times your weight. That's why you get squished down into the seat. Okay? Pilots, when they go up in the fighter jets, they make really tight turns. Sometimes they can pull 8 or 9 G's, which is really hard on the body. But those G's, that's where that G comes from right there. So let's do our calculation for our problem right here. We'll change colors here a little bit. And we're going to be using our acceleration is equal to VF minus VI divided by T. Now we did this the other week. And that acceleration right there, remember, is our special acceleration. Anytime you got a vertical problem, whether going up or down, gravity is always working. So that means that acceleration right there is always going to be G. And that's for up and down problems, whether objects going up or down, acceleration is always going to be G, or negative 9.8. All right, so here we go. Where's our numbers? G is negative 9.8. The final velocity, they want to know what the final velocity is going to be after 7 seconds. Now in this example right here, I went down to about 2 seconds. But if this thing kept on going farther and farther and farther and farther, how fast is it going to be going after 7 seconds? Well, let's see, the final velocity, that's what they want us to find. What is the velocity when it arrives at the ground? In other words, when it's way down here, what is that velocity going to be? So we don't know. So we're going to put VF back in there. VI, remember when you first let go of that rock, the initial velocity was 0. So that's going to make that a little easier. And the amount of time we're going to let this thing drop is 7 seconds. So we put a 7 right there. Now let's simplify this down a little bit. Negative 9.8. VF minus 0 is just VF. 7 is still down here. Now we've got to get rid of that 7. It's in the denominator, so we're going to have to, since you're dividing by 7, you've got to do the opposite, multiply by 7. So these 7's cancel out, leaves you with VF is equal to 7 times 9.8. Okay, so 7 times 9.8 is going to give us, let me look this up here, negative 68. Negative 68.6. Now this is the velocity, so this is meters per second. Now take a good look. I got a negative on there. Some people don't like it when the number answer comes out to be negative. But what does that negative mean to us in physics? In physics, it always means direction. And negative means down. Does that make sense? Yeah, our rock was going down. So right before it hit the ground, it was going negative, which is downward 68.6 meters per second. So there's the answer for the first one. Okay? You should definitely know how to be able to do this simple example right here, where you first have something, you drop it, it falls for a certain amount of time, and you can calculate the final velocity right when it reaches the ground. All right, next example, our last one, is what happens if you're throwing something up in the air. Because remember, acceleration to gravity. Gravity always works whether something is going up or down, because gravity never gets turned off. So as soon as this gentleman right here throws this ball and it leaves his hand, gravity is pulling on that ball the whole time. So at first, the velocity might be really high, but as that thing goes up, the velocity is getting smaller and smaller until right up here. Of course, at the very top, it comes up and it stops. Right? It stops right at the very peak up there. That peak up there is called the apex. Okay? Something new to throw at you. No pun intended. So the ball goes up, It slows down, slows down, slows down, slows down. It stops, and then, of course, in your experience, of course, the ball is going to come back down, go faster, 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 just like the Brock problem just finished. We're just going to analyze the ball from down here when he first throws it until it goes all the way up, and it reaches that point where it's going to stop. Now, up there at the top, that velocity up there, of course, again, is going to be 0. The initial velocity down here, they said in the problem, the ball is thrown up in the air with an initial velocity of 45 meters per second. So initial velocity is 45 meters per second. And notice that's positive. There's no negative sign on there. So that means he must have been throwing it positive, in the positive direction, upward. Okay, so that makes sense. And then it wants to know how much time. So how much time is this going to take for that to go all the way up there? All right. So let's do this calculation here. We're talking about an acceleration problem. We've got one velocity at 45. We've got another one at 0. So velocity is changing, okay, over time. Now this is my initial velocity when it goes all the way up to the apex and then it stops. That's going to be my final velocity right there. So we're going to use our acceleration problem again. So write down the acceleration formula. A is equal to VF minus VI divided by T. Now, look at that acceleration. Is this a vertical problem? Is this about something going up or down? Sure is. The ball's going up in the air. So that means this acceleration here is automatically going to be G. Okay? And we know from the last problem that G is always, on Earth, going to be negative 9.8. Okay? Always negative 9.8. So let's fill in the rest of the numbers. VF, the final velocity up there at the top of the apex, is 0 minus the initial velocity. They said right down here is going to be 45. And then divided by the time. Well, we don't know what the time is, so we're going to leave T right there. Let's simplify this thing. We have negative 9.8 over here. 0 minus 45 is just negative 45. And that's divided by T. Now, you got to find out what T is. Now remember, anytime you're trying to find something that's in the downstairs, it's in the denominator, you got to get it out of there. And the best way to do that is to cross multiply divide. So we're going to cross multiply and then divide. Okay, we're going to cross multiply and divide. So T times negative 9.8 is just going to be negative 9.8 times T. And remember down below this 9.8 is we assume there's a 1. So 1 times negative 45 is just negative 45. And now the divide part. We're going to divide by what's next to that variable, which is the negative 9.8. So we're going to divide both sides by negative 9.8. And the reason why we did that is because now you got 9.8, negative 9.8 on the top, 1 on the bottom. It cross out. It kind of gets rid of it for us. It leaves T all by itself. So to find T, we got to take negative 45 divided by negative 9.8, and you're going to get a positive 4.6 seconds. Okay? A positive 4.6 seconds. Now ask yourself if that's right. We came up with a positive number. And, well, you got to ask yourself, does time have a direction? No, that's always positive. Time's always positive. You can't have a negative time on there. Okay? Usually if you come up with trying to solve for time and you wind up with a negative answer, that means we probably forgot to put a negative up here in the formula somewhere, or we got something set up wrong. Okay? So always use that as a good double check method. All right. If you have any questions, be sure to email me. It's been good talking with you today. I'll see you later.